Okay, so next topic I'm going to talk about is to do with charge and current, which are really important ideas in electric circuits, which is going to be a really big topic that we're going to look at for the A level. So, first thing we need to do is make sure that our ideas about electric circuits are correct. Because very often, once you go through GCSE science, you can pick up some ideas about electric circuits that aren't quite true. So just to help you think about this, I just want you to think about this question. So, how long after I plug in a bulb will it take for the light to come on? Think of it as how long from when I close the circuit does it take for a light bulb to come on. So, hopefully, you'd all pretty much say that it would come on immediately, because that's what does happen, it instantly turns on. But what if it were further away? I bet a lot of you kind of think that if I made the light bulb far enough away from the power source, that there might be a little bit of a delay between turning it on and the light actually turning on. But the answer is, in fact, it doesn't matter how far away it is, it'll turn on immediately. Even if I could run wires from here to the moon, the moment I completed that circuit, the bulb would turn on immediately. And the reason for that is because the moment I connect the power pack to the bulb, the current begins to flow. That's an instant thing. The current immediately begins to flow. And the current is the rate of flow of charge. So as soon as I start moving the charge around inside the circuit, I can start operating devices in my circuit. So what we need to then think about is, how is that charge being moved around the circuit? Where's that charge coming from? Where's it going to? Well, if we think about the metal wires, what we know is that there are loads of electrons in there. They're loosely bound to the positive ions that make up the wire, but because it's a metal, those electrons are free to move. Sometimes it gets referred to as there being a sea of electrons. So when I turn the power pack on, every single one of those electrons in those wires start moving all at the same time and in the same direction. So they all start moving together. So that means that even the electrons that are in the light bulb, which is, on the moon and my power source was on Earth, it doesn't matter because all the electrons start moving at the same time, so the bulb instantly lights up. What a lot of you probably used to think was that it was something to do with electrons had to go from the power source to the light bulb in order for the light to turn on. But that's not the case. It's just that the electrons in the wires have to start moving, which is why it's an immediate thing. So, I said flow of charge. Well, often, and I've probably already said electrons, when we think about current flow, we do often talk about it being electrons now, and in most electric circuits that's true. It is electrons that are moving, but it doesn't have to be electrons. Charge can be carried by anything that has a charge on it. So I could have a positive ion that is also carrying charge, and that's what happens in electrolytes. So electrolytes are liquids that can carry a current. And if we just have a look at my diagram down here, I've got positive ions moving this way, and I've got negative ions moving this way, or electrons most likely. And that's absolutely fine. That works exactly the same as it would if it was just electrons. Okay, so we've got the idea that there is charge being moved, and the rate of flow of charge is current. So what we need to now think about is which way around does the current go. So, first thing we need to do is make sure that we know what this symbol actually means. Now, hopefully you all know that this is the symbol for a power supply or a cell. But the reason we have a long, thin side and a short, fat side is because one side is positive and one side is negative. So we draw them differently so you can tell the difference. And you do need to know which is which. So, the one on the left, the long and thin, is the positive. The one on the right is negative. The way I remember it, it's probably politically horribly incorrect, but if you are tall and thin, you're probably a bit more positive about life than if you're short and fat. I don't really believe that. It's just a way to remember which is positive and which is negative, because you do need to know. So if I've got a positive terminal and a negative terminal, my electrons are going to flow from negative to positive. But if you're asked about current, the direction in which current flows, sometimes also called conventional current, we consider it to flow from positive to negative. Okay, so in an electric circuit, electric current flows from positive to negative. So the direction of current is not the same as the direction that the electrons are moving. And it doesn't matter if there are no charge carriers flowing in that direction, current always flows from positive to negative. It's just a convention, it's the way we do it, it's kind of tradition, you can think of it as, but you do need to know that. If you're ever asked what is meant by conventional current, you say it's the flow of charge from positive to negative, because that is what's happening. There is a change of charge from positive to negative. It just might not be the way that you're thinking about it being. Okay? So, I've talked quite a lot about charge, and charge is really, really important. It's kind of a very fundamental concept in physics, but it may be something that you don't actually know that much about. So what do we know about charge? Well, we should know that there are two types of charge, positive and negative. We should know that like charges repel and unlike charges attract. Now, there's a very good reason I've used the phrasing like and unlike. I haven't said opposite charges attract, because in fact, whilst positive and negative charges do attract each other, positive and neutral charges also attract each other. So it's a much smaller effect, but that attraction is there. So using the term opposite doesn't give you all the information. That's why we start talking about like and unlike charges. So the reason we have positive charges is that you have more protons than electrons, and negative charges come from having more electrons than protons. Now, really important term here, charge is what we call quantized. And what that means is that charge comes in integer multiples. So basically, there is a smallest packet size of charge that you can get. And that amount of charge is the charge on an electron. You cannot get charge in smaller packets than the amount of charge on an electron. You can get multiples of that though. So you could get 3 lots of the charge of an electron, but you can't just get one. You can't get half the charge on an electron. It's kind of like buying packs of crisps. So if you want to go to the shop, you could go and buy yourself a single pack of crisps, or you could buy yourself a multi-pack of crisps, which has got 6 lots of the single packs of crisps. But if you go to the shop, they're not going to sell you a single crisp. They will only sell you them in multiples of a single pack of crisps. Okay? And really important, one of the most fundamental laws in physics is that charge is conserved. This is one of those absolutely, truly fundamental laws that's true for the entire of the universe as far as we know. And if this were not true, the universe would be unimaginably different. You might not be able to consider that just yet, but it is very true. And I'm saying this in a universe where later on we'll talk about the fact that particles can sort of just pop into existence, and that's absolutely fine, as long as charge is conserved. Okay, so what is the charge of an electron? What is this elementary charge? Well, it is 1.6 times 10 to the minus 19 C. Hopefully we all know that the C does not stand for charge, it stands for coulombs. So what is 1 coulomb? Well, 1 coulomb is the amount of charge which flows past a point in a circuit in a time of 1 second when the current is 1 amp. It's one of the definitions that you need to learn. Remember, this is a definition for a unit, not a quantity. So if we think a little bit more about the quantities then, so far we've got current, we've got charge, and we've got time, just by that definition. So I've got 1 coulomb as the amount of charge which flows past a point in a time of 1 second when the current is 1 amp. So if we think about that, we can actually come up with an equation that would let us figure out how these 3 quantities are related. So just take a little second and see if you can come up with one. And I'll give you the answer in a moment, don't worry. Whilst you're doing that, please also try and think that you need to remember to use symbols, not units here. Because otherwise, I mean, if you don't really think about it, you can end up thinking that you've got charge and current, so both of those are going to be C's. They are not. Make sure you pick the right letters. Okay, that's enough of me trying to fill time. So the equation we get is that current equals charge per time, or the change in charge over the change in time. So we make sure that current's measured in amps, the amount of charge is measured in coulombs, and the time is measured in seconds. And obviously then we can rearrange. Okay, so that is the basics for electric circuits, the basis on charge and current. So remember, if you have any questions, just ask when you see me.